Hello everyone, in this video we'll finish our databus demultiplexing circuit by improving some of the timings and making it work better. I hope you enjoy! So in the past few videos we've been looking at this bank address latching circuit and databus demultiplexing circuit from the datasheet. We've implemented it on a breadboard and we've improved the logic behind it so that it supports more use cases, namely around the ready and the bus enable pins. And I think we now have a pretty good grasp of the logic behind this circuit. There are no more CPU modes that we could add to this circuit. And so now I want to focus on the timing diagrams. So we've been building those timing diagrams as we went. This is the one for the latch and this is the one for the buffer. And so the first thing I did is I actually switched software in order to draw those diagrams. I'm now using a software called Wavedrom, which is a digital timing diagram software. There's a tutorial on the website that you can look at. And as you can see, there's some language that you have to use in order to draw any number of shapes that you want. And I've made a bunch of modifications to it in order to be able to create the diagram that I wanted. So if you try to reproduce these at home, please know that I'm not using the mainline source, but my own fork. I'm going to try to upstream all the changes that I do as much as possible. But this is how it looks like now. So this is the identical timing diagrams that we had before, just redrawn with Wavedrom. Okay, so let's talk about what we want to achieve here. I've mentioned in the past that the buffer output enable comes a bit too fast after the falling edge of the clock. You can see here that the buffer could start to turn off after 3 nanoseconds. And we are writing data up until 11 nanoseconds after the falling edge of the clock. And so it's possible that at some point here, the buffer would turn off and then we would lose some of the data that we were writing. And similarly, on the rising edge of the clock, there's also a delay of 3 nanoseconds, but the bank address is being driven on the bus for 10 nanoseconds, which means that we could create some bus contention if we were to enable the buffer too fast. So basically what I want to do is see if we can shift the signal to the right. So the first thing I want to do is to talk about the buffer a bit, and more specifically its output levels. So as you may know, there are two types of logic families in the 74 series chips. You have the TTL logic and the CMOS logic, and they have different input and output levels. The TTL logic, for example, can output a high level, which is as low as 2.4 volts. And this will be registered at the input because anything above 2 volts is registered as a 1. Whereas the CMOS logic will output 3.85 volts at a minimum for a high level, and that will be registered as a 1 because at the input, anything above 3.15 volts is registered as a 1. So you may notice that on both those families, the output levels are closer to 5 volts and ground than the input levels. And so this means that if there's some noise or resistance on the line, we are sure that chaining together 2 TTL gates or 2 CMOS gates will work properly. The problem comes when you start to mix those families. And if you look at the voltages, you can see that a CMOS gate driving a TTL gate is okay because the CMOS will output only as low as 3.85 volts, which will be correctly registered as a 1 by the TTL gate. And similarly, for a low level, the maximum it can output is 0.35 volts, which will also be registered as a low by the TTL gate. But a TTL gate driving a CMOS gate is not okay because the TTL gate will output as low as 2.4 volts for high level, which is in the undefined zone of the CMOS gate. And so we don't actually know if the CMOS gate would register this as a 1 or as a 0. And so even though this would probably work in most cases, because the TTL gate would rarely ever output something as low as 2.4 volts. It could be an edge case depending on the temperature or your specific chip or the current you're drawing where this would not work. And so if we look at the output levels of our buffer and one of the chips I want to use, which is the 71256SA RAM chip, you can see that the RAM chip actually has TTL levels. And so similarly, going from the buffer, which is a CMOS gate, to the RAM works out okay, but going from the RAM to the buffer doesn't actually work because the RAM is TTL level. The way to fix that is to switch to a 74ACT245, which has TTL input levels and CMOS output levels, which means that it will still be compatible with our CPU on its outputs, but it will actually translate the TTL levels from the RAM at the input. So if we look at the datasheet for the 74ACT245 in the switching characteristics, we can see that it's a bit slower than the 74AC245. So let me update the timing diagram to reflect this. So this is with the AC chip, and this is with the ACT chip. Okay, so now that we got that out of the way, let's see what we can do about shifting this output enabled signal to the right so that the behavior of the buffer is a bit better. So it's pretty easy to create a digital delay using a chain of logic gates, for example, 2 inverters or 2 AND gates chained together. However, doing it this way is not very precise. And since we're dealing with tolerances in the nanoseconds, I wanted to find a better way. And so if you look, for example, at Mauser's websites, in the delay lines / timing elements category, you can find this chip, the DS1135Z, which is a precise silicon delay line. Specifically, it delays the input signal for 10 nanoseconds. So if you look at the data sheets for the DS1135, you can see that you can find any number of nanosecond delay that you want with very tight tolerances. And so that seemed like a really interesting chip for our problem. We could get one with a 10 nanosecond delay here, and it will delay the output enable of our buffer. However, the only issue with it is it's a surface mount chip, and one of the goals of my project is to use only through-hole chips. So I'm personally choosing not to use this one, but if you look at the description, you can see that it's actually replacing 2 other chips. And for example, if you pull the datasheet for the DS1035, you can see that it's exactly the same chip, but it's the previous generation. And this one is available as a DIP package. So this one I could use. It also exists in a 10 nanosecond version, but the problem is this chip is obsolete. So you can't really find it new in any electronics dealer. However, I was able to find some used DS1035 on UTsource in a DIP format. So this is what I'm going to use. If you're not able to find these, you can always go with the 1135 with through-hole adapter, which means you could use it on breadboard. But anyway, the DS1035 is the one I'm going to use. So it's a high-speed delay line. You can see that there are 3 independent delays, and if you look at the data sheets, you can see that for the 10 nanosecond version, there's an initial tolerance of plus or minus 1.5 nanoseconds, and then this can be extended by plus or minus 1 nanoseconds over temperature and voltage range. So the total uncertainty is plus or minus 2.5 nanoseconds. So let's think about how we can use it in our circuit to make the buffer behavior better. So if I look at the KiCad schematic, you can see that what we actually want to delay is this signal here, the output enable of the buffer, and the signal is actually coming from the inverted clock. So let me make a bit of space here so we can see what we're doing better. We probably want to separate then the latch enable signal from the buffer output enable signal. So we're going to need another AND gate here. So we should have one spare AND gate here that we can use. And this takes the inverted clock and also our ready signal. Okay, so if we add our DS1035 here before the clock, so you can't actually find the DS1035 in KiCad's library, but I made my own symbol. I should probably add the 10 nanosecond number here and annotate. And we have one more power supply to add and the coupling capacitor. Okay, so now we have delayed the buffer output enable by 10 nanoseconds. Let's see how it impacts the timing diagram. Okay, so this is our timing diagram before. Let me add the shifted clock signal. There you go. So I'm naming this clock plus. It's shifted by 10 nanoseconds with an uncertainty of plus or minus 2.5 nanoseconds. Let's see how it impacts the behavior of the buffer. This is the buffer before being shifted, and this is the buffer after being shifted. You can see that now the buffer is enabled a bit longer after the falling edge of the clock, and it's disabled a bit longer after the rising edge of the clock. And so in a read cycle, you can see that it's actually on when the CPU is reading on both sides. In the write cycle, you can see that it's mostly on when we are writing data to the RAM. And I'm saying mostly because the difference is 0.5 nanoseconds. So yeah, I think I'm fine losing 0.5 nanoseconds of write data. So yeah, so this is much better. So the only issue that I see now is that we've introduced a lot of uncertainty around here where the buffer turns off. You can see that the CPU is starting to drive the bank address at a maximum of 33 nanoseconds after the falling edge of the clock. So it's probably going to happen a bit before, maybe right here in the middle. And at this point, we haven't yet turned off the buffer. So I would like to be able to reduce this interval. However, I haven't been able to find a solution using discrete logic gates. There's an easy solution, which is to switch to programmable logic for this. But this is not what I want to do for the first revision of the board. And yeah, with simple logic, I haven't been able to shorten this interval here. If you guys have an idea, let me know in the comments. But yeah, I think it's going to be fine. There's probably going to be a bit of bus contention, but we can probably live with it. Now, the other thing I want to fix is the opening of the latch. Around here, I would like to shift this rising edge here to the right around 10 nanoseconds so that the bank address is available 10 nanoseconds after the falling edge of the clock, just like any other address pin. So let's see how we can use this new shifted clock in order to do that. So one thing we have to pay attention to is this rising edge of the clock here. We have pretty tight tolerances when it comes to latching the bank address. It's only available 10 nanoseconds after the rising edge of the clock. And the AND gate that we use for the signal has a 7.5 nanosecond propagation delay. So ideally, we don't want to touch this at all, but just impact the falling edge of the clock here. So if we look at the signals that we have the clock here, and we have the shifted clock. So I just shifted it by 1 unit in this diagram here. And the signal that we want to build is this one. Its rising edge is shifted to the right 1 unit, but its falling edge is identical to the one of the clock. And if you look at this, the way to do this is simply by ANDing the inverse of both signals. We want the latch enable to be 1 when both the clock and the shifted clock are 0. So this is what we have to build. Let's build it in KiCad first. So we're going to need another AND gate here for the shifted clock signal. Thankfully, we have a bunch here that we can use. So it's going to take the inverted clock on one side and the shifted inverted clock on the other side. So that's what we want to build. However, one issue with it is that we now have 2 gates between the clock and the latch enable signal, and so our propagation delays are going to be much larger, and so that's not going to work with the latching. But we can replace both those AND gates with a 3-input AND gate, the 74AC11. And in order to save on the number of chips that we use, I'm going to replace all our AND gates with the 3-input AND gates. You can turn a 3-input AND gate into a 2-input one just by tying one of the inputs to VCC. So there you go. This is the new latch enable signal. If we take a look at the datasheet for the 74IC11, you can see in the switching characteristics that it has identical propagation delays compared to the AND gate that we were using before. So there are no changes there. However, we need to add the new shifted signal to a timing diagram. So this is the latch enable signal before we made the modification. And this is the latch enable signal after we made the modification. So you can see that the rising edge of the clock is not impacted because the new gate has the same propagation delays. So latching the bank address is still working fine. But the bank address is actually available now up until 10.5 nanoseconds after the falling edge of the clock. So it works similarly to other address pens. And the uncertainty around where the latch that is passing through what's on the data bus has been increased, but I think we can live with that. So yeah, so this is looking much better now. I'm pretty happy with the current timing diagram that we have. So there's still the issue of the buffer turning off too late in the cycle, but I think we can live with that. And so yeah, so I'm going to call this circuit done. Let's implement those changes on the breadboard. Okay, so the first thing I want to do is to take a look at those DS1035 chips, which I've got here. I've got a bunch of them. Let's take one of them and plug it into a breadboard so we can see how it works. So it needs power and ground. Let me get my power supply here. I'm going to use my square wave generator that I built as a previous project to create a square wave, and we're going to watch on the oscilloscope what it looks like. So it's going to go on the first input. Let me get my scopes. So the yellow channel is going to be the input and the blue channel is going to be the output. There we go. My power input is in the wrong pin. There we go, that's much better. So let's take a look at the oscilloscope. So you can see in yellow, this is the input signal. So we can see that the blue signal in output follows it pretty closely. And if we zoom in, we're going to be able to see the delay. So here you can see that the output signal is delayed by around 1 division, and my scale is 10 nanosecond by division. So this should be what we want. Let me actually measure this precisely. Let's measure the delay between channel 1 and channel 3. So there you go. So you can see that we're measuring at this moment 11.6 nanoseconds. So this chip is a bit on the slow side. Let me try another one. Remember that we are targeting 10 nanoseconds delay. So yeah, this one is much better at around 10 nanoseconds. And that's the one we're going to use. Let me just also confirm that all the inputs work. I did get this chip used, so I want to make sure that everything works properly. Yeah, all the input work. Perfect. Let's add it to our breadboard and take it from there. Okay, so this is our breadboard where we left off the last time. Let's add the 1035. It needs power and ground, as well as a decoupling capacitor. I'm also going to tie all the unused inputs of the chip high. There we go. And now we need to bring our inverted clock, which is over here, over here. Next, we need to replace this quad AND gate with a triple 3-input AND gate. So let me remove this one. And I have here 74 HCT11. So the power and ground inputs don't have to change. It also already has a coupling capacitor. We just need to make sure that the AND gates are properly populated. So let me disconnect everything that was connected to this gate. So the inverted clock we don't need anymore. We're going to take it from our DS1035. Here is the ready signal. And here is the latch enable signal. Okay, so let's have a think about this. For the simpler one, which is the buffer output enable, we're going to need to tie pin 3 to VCC. Here you go. So I just noticed that my wires here are not going to the right place. This should be going to VCC. Then we're going to need our delayed clock signal on pin 5. And on pin 4, we're going to need the ready signal. And then pin number 6 is going to the OR gate. So this is the buffer output enable done. We need to bring the inverted clock to pin 1 and the delayed clock to pin 2 for the latch enable signal. Okay, so now the only thing remaining is connecting the latch enable signal to pin 12. Okay, so this is all the modifications done. We should now be able to test it. We haven't tested the changes from the previous video as well, so I want to do that now. So the first thing I want to do is to tie all the unused inputs of the CPU high so that they don't break the test that I'm going to do. So I'm going to tie reset, which is pin 40, as well as all the interrupts, which are pin 3, 4, and 6. To VCC. Then I'm going to take the CPU off the bus by taking bus enable low. Bus enable is the orange wire here. And then I'm going to bring in my power supply. Okay, so the first thing I want to measure is the ready pull-up again, because I didn't do it very precisely last time, and I want to build a timing diagram for it. So I'm going to bring in my clock generator again. and feed the clock into the clock multiplier. Then I'm going to add a button that will pull down the ready input when I press it. And I'm going to add my probes. So in yellow is going to be the clock. And in blue is going to be the... First, let's look at the button for now. Okay, so now if I don't press it, it's high. And if I press it, it becomes low. Okay, so let's look at the registered ready in. Now it should only change on a clock. So let me change the triggering setup. I need to trigger on channel 3. Let me do a single one. Falling slope. There you go. So this only changes on the rising edge of the clock. And now I want to measure the delay when I enable ready and disable it with the ready pin of the CPU, basically what happens through the diode. So in blue is going to be the input, and in yellow is going to be what the CPU sees. So let me do another single capture. I changed the wrong yellow wire. Okay, so when ready is brought low, the signals are perfectly synchronized because the diode is just letting the current pass through. Now let's look at what happens when I release ready, because that's when we have some capacitance on the line. There we go. So this is the rising edge. So we can see that there's some capacitance being discharged on the yellow signal, but it's transitioning pretty quickly. Now the question is, when does the CPU recognizes the ready input changes? The CPU actually registers a change of input at VDD times 0.8. That's 4 volts. So what happens at 4 volts? I would say around 30 nanoseconds. It takes to register the change, which is nice because it fits into one of our clock cycles. Okay, so this is the first thing I want to measure. Now let's test the behavior of our control logic as it relates to the ready pin. So let me remove my probes and my button. We're not going to need the clock, so I'm going to tie it back high to VCC. Okay, so let me bring back the test circuit that we built in a previous video. Okay, so I'm going to use this button here for the clock. It's active high. And for now, let's tie ready to VCC. Okay, so I figured out the problem after a bunch of troubleshooting. I've tied the read-write line low, so we're in write cycle. I've also added LED to the clock output so that we can see the clock phase that we're on. Since we now have the frequency divider, it's not just the button that we're pressing. And I think I was missing a resistor here. But we should be ready to go now. So the clock is now low, so the latch should be transparent. And anything I change on the input should be reflected at the output. Now, if I transition the clock, the bank address is latch, and we see what's on the bus on the data bus output. So if I now change the dip switch, this should be reflected on the data bus output, but not the bank address. So our basic circuit is still working. Now, if I take my ready input low, nothing to change because we're now in a high phase of the clock. So I need to transition it once so it's low, and one more so that now we have latched the ready input, and so ready is low. And so now whatever I do with the clock, we should always be in a data transfer state. So this should always be outputting. And this seems to work as well. Perfect. And now for completeness, if I take bus enable low everything should disappear. Yeah, and our bank address is being pulled high currently, and the data bus is being pulled low, so this is correct. Let's remove the test rig and put back the CPU and restore our signals. So bus enable high, bring the clock low and ready high, and then remove the read-write line that we had tied low, and then we can put back the CPU. And there we go. So this is our new completed circuit. So we have come a long way from the single inverter used in the circuit from the datasheet to the more complex circuit that we have now. But I think it's for the best. The circuit that we have now has correct timings. It works with more CPU modes, with bus enable and stopping the CPU using ready. And we also added the wait outputs. So I'm pretty happy with the circuit that we have now. I don't see any improvements that I could make to it, besides eventually switching to programmable logic. So I'm going to call this down for now, and in the next video, we'll go back to basics and work on the clock. So I hope you enjoyed this video. Let me know in the comments if you have any comments or feedback, and I hope to see you in the next one. Bye.